In this tutorial, you'll learn how to model a complete reinforced concrete structure in ideCAD Structural, from axis definition to raft foundation creation. We'll start by placing axes using snapping tools and contour lines for precise alignment. Then, you'll see how to model rectangular and polygon columns, and configure each with accurate dimensions and materials. Next, we'll define shear walls with dynamic delta control, group wall assignment, and reinforcement design options. You'll learn how to draw beams across axes and columns, adjust delta elevation, and apply key structural and reinforcement settings. We'll continue by creating slabs, both standard and cantilevered. After that, you'll define additional stories, copy modeled elements across floors, and configure rigid basement shear walls. Finally, we'll wrap up by modeling a raft foundation using route paths, offsets, and full structural detailing. By the end of this video, you'll be able to model all major structural elements with precision and confidence using ideCAD. Now that I know the units are correct, I can directly start axis modeling. First, I click the Axis tool. I go to the Concrete tab and click the Axis box. As you can see, a floating axis toolbar opens on the screen. On the Axis toolbar, we can draw our axes between the contour lines. To adjust the contour drawings according to the drawing, I click the Contour Lines box below the Axis toolbar. Here, I can define the contour so that it stays inside the drawing area. In this way, I set the contour lines and leave them within the drawing. I now return to the Axis tool. At this point, I can press the spacebar on the keyboard, or use the Axis Driving Type button in the toolbar to change the orientation of the axis. As you can see, the axis is currently horizontal. If I press the spacebar again, it switches, and pressing it once more returns it to the initial axis mode. To define the first axis, you can assign it between any 2 points. If we didn't have a drawing under the screen, and after defining the first axis, we pressed the Enter key, the program would define axes automatically using the current offset value, for example, 1 meter, as shown in the toolbar. If I typed 500 from the keyboard and pressed Enter, it would define the axes every 5 meters apart automatically. But right now, we don't need to define axes this way, because we are working on top of a reference drawing, and the positions of the axes are already known. So, we will define the axes by aligning them with the drawing. While positioning the axes, we can use the Advanced Snap feature. In this program, as you can see, when we press the Control key, the feature is also activated in the toolbar. By holding Control, I can snap directly to the points. And in this way, I can define the axes quickly and precisely. When I press spacebar again, I switch back to horizontal axis direction. I then define the first axis by clicking a start point and an end point. And again for the second axis, start point and end point. This is how we define our axes. If we click the gear icon on the left side of any toolbar, the settings menu for that element will open. Now, if we talk about axis settings, in the available settings we can change the axis ID, and also change the line types. In the axis border section, we can edit the left and right delta values. In the label section, we can adjust the label radius, label text height, label color, text color, and choose the font. In the info text section, under axis distance to origin, we can activate and define the distance and height values. We can also define the base units, and set the digit count as needed. This is how we define and configure axes in the program. Now, let's define the columns in the program. To define columns, I click on the Column command under the Concrete tab. In the toolbar that opens, there are 3 options: rectangular column, circular column, and polygon column. I click on the rectangular column option. Here, we see the column alignment settings: corner align column, left middle align column, centered column, and default align column. These options let us choose from where the column will be aligned during modeling. In the input boxes, we can enter the column dimensions. Since our column is 60 by 30 centimeters, I type in 60 by 30. I choose the corner align column option to place it. Now, since we are at the intersection of two axes, the column snaps automatically to the node point. I pull the column down toward the lower axis. Right now, the column appears reversed. I press the spacebar on the keyboard to mirror the column and place it correctly. I will model the other columns using the same method. I snap to the axis point, press spacebar, and the column is mirrored. For the next column, I do the same, snap and press spacebar. And again, snap, spacebar, and place. This is how I model my columns. Here, I have a column with a different size, a polygon column. I start modeling from this point, drag downward, and press the spacebar. In Drawing Underlay, you can see a polygon column. To create a polygon column in the program, start by right-clicking on an existing column. From the context menu that appears, choose the Trim Column command. The Trim command allows you to both trim and extend a column. Based on the edge of the axis you select, the software knows whether to trim or extend the column in that direction. In this case, we want to extend the column. So, first click the edge of the column that needs to be extended. Then, click on the axis to which you want the column to reach. Once you complete these steps, the column will be reshaped, and a polygon column will be generated accordingly. Here, I also have a column with dimensions 80 by 30. I open the column command and enter 80 by 30. Since there's no axis above this point, I use snapping. I press the Control key to activate Advanced Snap. Then I click the top point and the bottom point, pressing spacebar as needed. And the column is correctly placed on the natural node. Next, I want to design a polygon column. To do this, I go to the Drawings tab and use the Multiple Lines command. While holding Control, I draw lines around the polygon column shape. To enable the Advanced Snap feature while drawing, simply hold down the Control key on your keyboard. After creating the multiple lines, I select them from left to right, then right-click and choose Transform to Polygon Column. This defines the polygon column. Now let's talk about column settings. To access them, we can first select all columns and click the column icon under the Concrete tab. Or we can click on the column settings icon before modeling. In the General section, we can see the column ID. Under Dimensions, we can define the width, height, delta x and y values, upper elevation, and inclination length. In the Text section, we can set how the ID and dimension texts appear in application or formwork plans. We can adjust the text coordinates here as well. In the Structural Concrete section, we choose the material for the column. We can enable override section parameters if needed. If there is a sub-basement level, you can let the program calculate it, or enter it manually. If there is jacketing, you can define the jacketing thickness, material, and anchorage settings. If you are designing for punching in flat slabs, you can assign punching reinforcements here. Similarly, for foundations, punching options are available. You can also assign components to the column if necessary. To create shear walls, I click on the shear wall icon under the Concrete tab. In the toolbar that opens, I select the Draw Shear Wall command. And I can draw the wall on the drawing base where the shear wall is shown. To start drawing, I press the Control key to activate the Advanced Snap feature. When I press Control, the snap becomes active both on the keyboard and in the Snap panel. While adjusting the delta direction, I can press the spacebar to control the angle or orientation dynamically. This allows me to draw a three-legged shear wall. After drawing it, I select all three legs, and then open the shear wall properties. I can do this by pressing Ctrl+E or by right-clicking the wall and choosing Properties. Let's now go over the shear wall settings. Since we selected a three-legged wall, the settings we apply will affect all three parts. In the General section, we can see the name of the shear wall. Because this is a group wall, we need to assign a group name. I enter G1 as the name. Thicknesses, elevation, and upper elevation can all be adjusted from this menu. We previously used the spacebar to set delta directions. And now we can choose between top, middle, bottom, and user-defined delta settings. In the Text tab, we can customize coordinate display, combined ID, and dimension text that appears in the drawing. In the Structural Concrete section, you can select the structural material for the shear wall. You can also modify the finite element width properties here. If there is a sub-basement level, you can let the program calculate it or input a custom value with user-defined. If you're working with ACI, and using Use Crack Stiffness properties for shear wall, you can enable those options in this section as well. In the Thermal Parameters tab, you can assign thermal properties to the shear wall if needed. Under Stiffness Modifiers, you can set parameters like modulus of elasticity or moment of inertia by selecting the relevant modifier options. In the Reinforcement Design section, if the wall is intended for strengthening, you can activate Reinforcement Shear Wall and configure its detailing. The head length is calculated automatically, but if needed, you can switch to user-defined and manually enter left and right head lengths. If your grouped shear wall includes a short header wall, you can choose the short head shear wall option from the settings. In the objective field of Reinforcement Design, you can assign a design system such as basement shear wall, or choose geometry defined. Once reinforcement is activated, you can also configure anchorage settings for the wall's connections with beams and columns. Additionally, anchorage for jacketing reinforcement can be adjusted in the Reinforcement Jacket section. If you plan to use punching reinforcement, you can configure it in the Punching System and Punching Foundation tabs. You can also define wall-related components in the Components section as needed. These are the available properties for shear walls. That completes the walkthrough of this definition process. Now, we can create the beams in the program. To create beams, I click on the beam icon located in the Concrete tab under the Concrete section. When I click the beam icon, the beam toolbar appears. In this toolbar, I can use the Draw Multiple Beams command to draw my beams. Other options in the toolbar include curved beam, arc beam, circle beam, continuous arc beam, and connection beam. Here, I can define the width and height of the beam. I can also assign the beam load on the beam. Later, I will also explain the beam settings. While in the Draw Beam command, the program automatically snaps to the intersection point of two axes. When I move toward the second axis intersection, where the beam should end, I click the left mouse button to create the beam. I can press the spacebar to adjust the delta offset of the beam. Once the offset is set, the beam is created. Let's now draw the next beam using the same method. To draw multiple beams at once, if I select the starting and ending points between columns, the program will automatically split the beam between those columns. This allows you to model beams quickly and efficiently. Similarly, if there is no axis between two columns, you can press Ctrl to activate Advanced Snap. To exit a command, you can press the Escape key on your keyboard. If you want to quickly return to the last command you exited, simply press the scroll wheel on your mouse. And define a beam directly between the two column nodes. Again, I adjust the delta using the spacebar. And where no axis exists, I use Ctrl and the advanced snap to place the beam accurately. This is how we create beams in the program. Now let's talk about beam properties. You can access beam settings by clicking the settings icon. In the beam settings, you can change the beam ID, beam width, and beam height, elevation, right delta elevation. As we did earlier using the spacebar, you can set the delta orientation as top, middle, bottom, or choose user-defined if needed. In the text settings, you can set text coordinates, combined identity, and dimension. In the structural concrete section, you can change the structural material of the beam. By enabling the override section parameter, you can manually configure additional section properties. If you plan to perform PMM design, you need to check the PMM design box. For the wall load entry, you can select a wall types from the library. Or define a custom value manually with user-defined. Likewise, for live load, you can select loads from the live load library, or define your own live load using the user-defined option. In the reinforcement design section, one of the most important parts is the bent-up bars parameter. If you want to design without using bent-up bars, you must enable the design without bent-up bars option. In the cracking and deflection tab, you can configure the cracking limit and the deflection control limit. If you want to define components, you can do so under the beam's component settings. These are the available beam configuration options in the program. To create a slab in the program, I click on the slab icon located in the concrete tab. In the toolbar that opens, I use the slab command to draw the slab. To draw a slab, we need a closed area. As shown in the figure, the program automatically detects the closed area formed by 4 columns and 4 beams. It automatically recognizes any closed zone surrounded by beams. When you move the mouse over these zones, the program visually previews the slab fill. And by clicking the left mouse button, you can create the slab. So, just clicking is enough to create slabs in these closed regions. In the case of cantilevers, where there are no beams forming a closed region, I will first draw slab edges using the slab edge command. These edges will define the slab boundary. Then, I will create the slab within this boundary. To draw the slab edge accurately, I press the Control key to activate Advanced Snap, and I snap to the desired point on the drawing base. Once the boundary is ready, I click the slab command again and create the slab within that outline. Here, I also have an angled edge. First, I draw the straight edges using the slab edge command. Then, I switch to the continuous slab edge command, and by selecting a start, middle, and end point, I draw the curved edge. Finally, I complete the boundary using the straight edge again. This way, I can define the slab fully, even with complex shapes. In the slabs I've just defined, you'll notice there are slab calculation axes labeled 1 and 2. You can modify these calculation axes by going to the Edit Concrete Calculation Line section. Here, under Reinforcement Type, you can switch between straight, bent up, upper, and under straight reinforcement options. If you want to apply these changes to multiple slabs at once, you can select all the slabs, press Ctrl+E, and access the slab settings window directly. In the General Settings, under the Dimension section, you can define the slab thickness and set the elevation. In the Load section, you can apply loads from standard codes or use user-defined values. You can assign these from your load libraries or enter them manually. In the Material section, you can choose the visual material, as well as the material table for the slab. In the Text section, you can control text placement for the slab ID in formwork plans. You can also define displacement parameters in the X and Y directions. If you are using a ribbed slab, you can configure ribbed annihilation settings under ribbed slab. If it's a waffle slab, you can set first rib and second rib under the waffle slab tab. In the structure section, you can choose the structural material and define the finite element width of the slab. Under the deflection tab, you can define the deflection limits of the slab. If you plan to use mesh wire reinforcement, you can enable the Use Mesh Wire option to apply it. In the Components section, you can assign components to slabs if needed. This is how you can define and model slabs in the program. Now that we have defined the axes, shear walls, beams, and columns, we can define the other stories and copy the current story to them. But first, we run a contour calculation to automatically generate axis deltas. To do this, under the Axis command, we click Calculate Contour. Then, since the imported DWG base was brought in as a block, we can now select and delete it from the model. After removing the base drawing, click the Story Settings command. In the Stories window that opens, use Add Above to add upper stories, or Add Below to add a basement floor. In the Stories section, the following fields appear. Live load factor, entered according to the code and project. Rigid, if the basement floor is considered rigid, check this box. Stair/machine room and index options are also available. If there is a machine room or stairwell on the top story, you should select this option. From the elevation and height fields, you can define the story height. When you click OK, the stories are created. After creating the stories, click on the Story Copy command under Story Settings. In the Story Copy window, select all the copy checkboxes and click OK. This action copies the elements from the current story to all the other stories. Next, go to the story list and open the basement level. First, delete the cantilever slabs. After deleting them, select the beams formed on the outer axis. As we want to create rigid basement walls along the building envelope, right-click and select Convert to Shear Wall. The selected beams are now converted into shear walls. Then, reselect these shear walls. Press Ctrl+E to open the shear wall properties. Go to the Reinforcement Design as Structural Concrete tab, and enable Subbasement Panel/Vertical Discontinuous Panel. If the shear wall is a subbasement shear wall or a shear wall that does not continue throughout the whole floor, this option is checked. When marked, the relevant shear wall is not included in the cutting area effective in alpha calculation. This completes the definition of basement walls. Since we're in the basement story, let's define the foundation, which will be a raft foundation. To create a raft foundation, we first draw the raft edge to define the boundary. This can be done using a path traced around the outer edge of the plan. Under the Drawing section, click the Route Path command, and draw a path along the structure's outer boundary. Then, click the Offset command under Drawings again, and offset the path by 50 cm. Now, using Raft Edge, we trace over the offset path to leave a 50 cm offset strip, and define the foundation boundary. After that, click on the Raft command, and click inside the defined raft edge area to generate the raft foundation. To enter the raft foundation properties, double-click on the foundation. This opens the raft foundation settings window. In the Dimensions tab, you can set thickness and elevation values. In the Load tab, you can apply coating load and live load, either from the load library or as user-defined. In the Materials tab, you can choose the visual material. In the Text tab, you can adjust circle, diameter, displacement in X and Y. Under the Structure section, You can define the structural material and the finite element width. In the Reinforcement Chair section, reinforcement chair settings can be specified. From the Component tab, you can also assign components to the raft foundation if needed. This completes the definition of the raft foundation in the project. Thanks for watching. Don't forget to like, subscribe, and explore the knowledge base for more tips. See you in the following video.